Hello everyone. My voice is audible. So, before we start, I just the previous session, some people had some confusion about the duality principle. So, let me tell what is the duality principle in the Fourier transformation once again, and just write the equations corresponding to that fact. Is suppose x of omega and x of t, this is in time domain. This is in frequency domain. So basically, these two has a relationship. The relationship is like if x of t is the Fourier transformation of x of omega, then we can write that x of t has a Fourier transformation, what is 2 pi small x of minus omega, and this big omega is in angular frequency, that is omega is equal to 2 pi f. This is the fact. Now this also can be represented as follows: x of t has a Fourier transformation, that is this x of minus f, if I am taking only frequency in hertz, and this omega is angular frequency, that is radian sort of thing. So basically I can prove this also in the following way. So we know what happens: xt is a time domain signal, then it has a frequency domain representation like this. Right. So for the sake of clarity and simplification, just keep this 2 pi xt is minus infinite to infinite x of omega e to the power j omega t d omega. Now we can write just the same equation but replace t as minus t. If we do so, it will be 2 pi x of minus t is equal to minus infinite to infinite x of omega e to the power minus j omega t d omega. So see, this is just a change of variable, but this sort of equation is the equation for inverse Fourier transform. For clarity, we can also write this equation like change t is t to omega and omega to t. Name of the variables I am only changing, nothing else. So that will be 2 pi x of minus omega is equal to minus infinite to infinite big X of t e to the power minus j omega t. So this is sort of inverse Fourier transformation. So from this we can conclude that Fourier transformation of x of t is 2 pi x of minus omega. And also the vice versa happens. So for such reason, this duality principle holds. Okay. So, example of such duality principle is, suppose we have a rect signal t by t with duration t, and we know it has the Fourier representation sinc of ft in angular frequency. Following this, if we want the function Fourier transformation of a signal like AT sinc of tt, this will have a Fourier transformation like this. Right? This minus sign just only comes and t is changed by f. The rest of the things are remains same. And the rect signal is a even signal. So for even signal, this negative of axis changing has no meaning. So this is actually a rect of f by t. So this t defines the time period. So based on this t and a, you can change any of the sinc function to any of the square function. And also someone asked what will happen in case of a triangular function. So if there is a triangular function with duration t, that means I have a signal that has a duration of these two values are t and the amplitude is a. This has a Fourier transformation of AT sinc square ft. Following this triangular wave function is also symmetric with respect to the 0. So that x of minus f is equal to x of f. These two values are same. Following this, we can write that if we have a time domain signal AT sinc square, tt that will have a representation a triangular minus f by t. That is equal to, this negative value has no meaning as the transformation or the triangular function is symmetric with respect to 0. So this is equal to a triangular function of f by t. That is all. Now, according to your requirement, you can change the value of t and change the value of a. So, for rect or normal sinc function, it comes like this, and for this sinc, it becomes this. So, these were the doubts of previous sessions. I think it is clear now. Okay. So, let us start the problems of week 4. That will be better. Okay. So, the first question of this week 4 is, consider the following signal. X of t, that is cos 2 pi fct. And then suppose the signal is passed through a multiplier, and the multiplier is not perfect, so this is passed through an imperfect multiplier. And what happens if it goes through the imperfect multiplier? It becomes yt is equal to cos of 2 pi fc plus del f t plus delta theta to the input signal x of t. So I have a signal xt and the signal is passed through an imperfect multiplier. That imperfect multiplier has the equation of this. So where is the imperfection mainly? Here is the imperfection, here is the imperfection. So the next statement is, if I sent this multiplied signal through a low pass filter, so if the output of the multiplier is passed through a low pass filter, then the average power of this multiplied signal, that is xt yt, is independent of del theta, and you have to comment whether it is true, the statement is true, or the statement is false. So once more, I'm just telling the question. The question says that we have a signal xt, that is cos 2 pi fct, and a signal then just goes through an imperfect multiplier. The imperfect multiplier is, here is a frequency imperfection and a phase imperfection. So after this, we get the output of this multiplier, that is xt into yt, is passed through a low pass filter, and then we obtain the average power of the output, and that average power of the output is independent of del theta. We have to comment whether this statement is true or this statement is false. So let us solve the question. So what is the output of the multiplier? That is zt. So what is zt? Zt is the multiplication of xt and y of t. So that is cos 2 pi fct. This is one signal, that is xt, into cos of 2 pi fc plus, let's write like this, fc plus del f t plus del theta. If we multiply these two signals, it will be like following the formula of cos A cos B is equivalent to cos of 2 pi into 2 fc plus del theta plus cos of del ft plus del theta. Okay, so this term is cos A and this whole term is cos B, and then from this cos A and cos B formulation we just derive this equation. So this is the signal zt, that is the output of the multiplier. So now zt is the output of the multiplier. So if we pass this particular ZT through a low pass filter, we will obtain another signal, that is Z1 of t, and that is, so let's see what is the signal. There is a component 2fc here. So 2fc contains a very high frequency. So the 2fc part, this will not pass through the low pass filter. Right? This part, if we apply a low pass filter, this part will not get passed through. But this part has a frequency of del f, right? Another part is of del f, small fluctuation, but it will go through the low pass filter. So the signal after LPF will be A by 2 cos del f t plus del theta, right? So if now del of f is not equal to 0, that means there is some imperfection in terms of frequency also, as this f del f term. In such scenario, what will be the power of this signal? So this is a cos function and its power does not depend on del theta, not depends on del f. And we know what will be the power of this signal, that is 1 by 8. So the conclusion is, the average power is independent of del theta. Oh, I forgot to mention what is A here. A is half. So this is the conclusion. The average power is always independent of del theta. So the statement is true, is independent of del theta. Yes, that option, the correct answer is true. Next question says, the output of an AM modulator is given as y of t is equal to 8 cos 3600 by t plus 32 cos 400 by t plus 8 cos 4400 by t. Now the signal can also be expressed as A into 1 plus mu cos 2 pi fm t into cos 2 pi fct, and fc is greater than fm. So we have to find what is fc and what is fm. Okay, so this question is pretty straightforward because y of t is given as 8 cos 3600 pi t plus 32 you can write your answer in the chat box also. 32 cos 4000 pi t plus 8 cos 4400 pi t. So first take these two terms. This is 8 cos 3600 pi t plus cos 4400 by t. Sorry, not this term, this term. This also has a 8 coefficient, right? So that is the simplicity. Plus 32 cos 400 by t. So this term is this term is this, and we are rearranging the terms. From this we can write this becomes 32. Just you can use the formula of cos a plus cos b. That formula you can use here, and it will come a function like 0.5 cos 400 by t into cos 4000 by t. And from here you can find that this is the Fm and this is the term that contains Fc. So 2 pi Fm is equal to 400 pi and Fm is equal to 200. Similarly, Fc is equal to 2000. So this is the way. If you have given this sort of signal, you have to decompose this signal and have to use the formulas to get this sort of equation. The next question is, for the same signal, what is the value of mu and what is the value of A? So value of A is also 32 and value of mu is 0.5. So modulation index, amplitude of the signal, message bandwidth and frequency, carrier frequency, all four terms can be derived from a given this sort of equation. You have to divide by 2 also. I think that is the problem for FM. You got the answer. That's why it was wrong. I don't know. This was Suraya. Okay. Let us move to the next question. The next question says, what is the sideband power? For this YT. So let's go back to this question once again. Just a minute, I'll be back. Soon. হ্যাঁ বল, কত করে পড়বে কুরিয়ারে? 200? ধর কি মনে হয় 200 কম পড়বে না? 200? হ্যাঁ তাহলে অসুবিধা নেই, 200 বেশি হলে পরে আমাকে যেতে হবে, 200 বেশিটা অনেক বেশি হয়ে যাবে। 3 দিন লাগে আসতে। হ্যাঁ করে দে, ওটাই ভালো সবচেয়ে। ওটা আমার কোনো অসুবিধা না, আমি ভাবছিলাম 500-600 টাকা নিয়ে নিলে অসুবিধা। ঠিক আছে, ঠিক আছে। So what will be the power, sideband power? So what is the message signal here? The message signal here is 32 into 0.5 cos 400 by t. This is the message signal here, right? So the question says, what is the sideband power actually? So what is the power of the message signal? Power of the message signal is 32 into 0.5 square by 2, that is 128. So power of the sideband will be 128 by 2, that is 64. The answer is 64 for this. Now the next question is, what is the power efficiency of the modulation scheme? Of this signal. So we know what is the sideband power, right? From this sideband power, we have obtained is 64. And what is the power of the carrier power? The carrier power is square by 2, where A is 32. So this is 512. So power efficiency, that is sideband power by sideband power plus carrier power, that is 1 by 9. Now let us move on to a new question. That is question number 6. This says if the modulation index of a M wave is increased from 0 to 1, then then what is the transmitted power? What is the transmitted power change? So option A is an increase by 12.5%. Option B is increase by 25%. Option C is increase. This is also increase. Option C is increase by 50%. Option D is none. So says the question is like the modulation index, that is mu, of the AM wave is increased from 0 to 1, and what happens to the transmitted power actually? Anyone here to answer this question? Okay, I think nobody has solved this. So when the modulation index is 0, then what is the power? P0 is only the carrier power. When the modulation index is 1, sorry, modulation index is 0.5, this P1 becomes c square by 2 into 1 plus square by 2. So if we compare this P1 by P0, is 1.50. This says this power has been increased by 50%. That is the value of mu. First time it is 0, this is 1. So the correct option is option C. The next question is, in an amplitude modulation scheme, the modulation envelope has a peak value which is 1.5 times the unmodulated carrier value. Question is, what is the modulation index? This is very simple question. This says the envelope has a peak value which is 1.5 times the unmodulated carrier value. So AC 1 by mu by AC, the actual envelope value, is 1.5. This is after modulation peak value with plus mu, and this is the only carrier value. From this we can get 1 plus mu is equal to 1.5, or mu is equal to 0.5. This is the answer. And the increase is about 50% here because of this 0.5. It becomes from 1 to 1.5. So a 50% increase happens due to modulation. let us go to the next question. The next question says a message signal MT is sync squared T, and this modulates the carrier signal CT as a cos 2 pi FCT. So you have to find out what is the bandwidth of the modulated signal. And obviously we use the notation of sync t as sin pi t by pi t. So I'm just telling you what is the hint of this question. That it is a signal xt that is just getting multiplied with mt ct, and this is a sine square t into cos 2 pi fct, right? So this is in time domain. So now we have to use the Fourier transformation properties. So what if we use the Fourier transformation properties and we say that this has representation of x of f, then the following thing we can write, that x of f, that is the Fourier transform of the signal, that is a by 2 into delta of f. Sorry, this is the, see, we have a sine square signal, they are multiplied in the time domain, so there will be a convolution in the frequency domain, and we know so there is a triangular function, and it will have a convolution with the cos. So cos has this sort of representation, f minus fc plus del of f plus fc. Okay, so for more simplification we can write it, this is just a convolution. So this triangular wave function will be moved to particular these two directions, and see what is the bandwidth of this triangular function is 1. So this is del of f minus fc plus del of f plus fc, because of this convolution property. So the first thing is f minus fc is not equal to 0, right? Because fc is greater than f. That is the main thing for a modulation. So from this we can say the modulated signal will have a bandwidth of 2 from this triangular functions. Okay. Now let us go to the last question of today's session. The last question says, consider we have a modulated signal in T. It has a mean value that is 0 and a max value a max, and this has a bandwidth of W m. So this is the bandwidth. So what we do, we have a MT of these characteristics, and this MT is first we add a circuit with cos omega c t. And then after this addition we get a signal xt. And xt is goes through a device that does this sort of operation. Suppose this is a non-linear device and this gives an output of yt, and this yt is alpha xt plus beta x squared t, and then it goes through a filter again. The output of the filter gives a M signal. So we have to comment whether this filter is low pass filter, high pass filter or band pass filter. And also we have to comment on the constants of f0 and w. So what will be the specification of the particular filter in this scenario, that we have to calculate so that this gives us a M modulated signal. Okay, so let's solve it. So what will be the signal yt? Yt is getting an input, that is summation of mt and cos omega ct, that is xt. So this is alpha xt plus beta x squared t. So alpha xt plus beta x squared t. this will be alpha. So what is xt? Xt is mt plus cos omega ct plus beta of mt plus cos omega ct square. So this is equivalent to beta m square t plus to beta mt plus alpha cos omega ct plus alpha mt plus beta cos square omega ct. So if we draw the frequency response, it will be like this. It will have a signal component of this sort of type. This is at minus 2 omega c. At 2 omega c. So why? Because this is a cos square signal, and this will have a simplification of cos of 2 omega ct. That part is here. We have a signal alpha mt, so this will have minus omega m to omega m. Also signal m square t, so that is minus 2 omega m to 2 omega m. And this signal will contain del pulse due to this alpha term cos omega ct, and of this due to this modulation with cos omega ct, it will have this sort of two pulses. So this is clear. So just make a color for this, so that will be easier. So this beta mt plus alpha cos omega ct due to this is this part, and this part. And these two is this part, right? And this is this part and this one. So we must design a bandpass filter so that signal that is centered around omega c, that is at omega c here and here omega c, can be extracted and all the other terms should be removed. So this should be a band pass filter. This sort of band pass filter. And it should not overlap with the baseband components. So the answer will be a band pass filter. It should be with center frequency at f0 and bandwidth of W such that f0 minus Wm is greater than f0 minus 0.5 W is greater than 2 Wm according to these conditions. This is omega c minus Wm and this is omega c plus Wm. We have to need a such sort of candidature. That is the reason bandwidth of W such that this is greater than this but not greater than 2 of Wm. So this should be the characteristics of this signal, of this filter. So this was all for today's session. So anybody has any doubt about today's session? Okay, then we'll meet in the next Sunday.
Thank you, sir.